So we've come to the last section that we're going to do in discrete structures, section 5.3. And the section is called Inclusion, Exclusion methods and binomial methods. And what it is it's going back to counting again. We did a little probability. We're going to use the probability, but we're going to go back to counting. Okay? Nothing hard, and it's just a nice, clever way of doing things. Okay, so let's remember. When we wanted to count all the elements in two sets, we have two sets, A and B. So what we do is the number of elements in A union B is equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. And I explained why, because if you count A, you're counting this once, and then you add it with B, you're counting that twice. Well, you don't want to add it twice, so you better subtract it. Great. Now, let's generalize this rule. Okay? And if you generalize it, you get, what about this? A union B union C. Okay? So let's draw a picture. Okay? A, B, and C. And I want to add up all the elements and see how many elements there are. Okay, so the rule is as follows. Well, let's just do it this way. I'm going to add up all the elements in A. Then I'm going to do all the elements in B. Okay, and then I'm going to do all the elements in C. Okay, so let's do that. That's the elements in A plus the elements in B plus the elements in C. But 1 second. I added A intersect B twice. That's why that has two things in there. So I better subtract it out once. So minus A intersect B. Same thing, B and C. I added them twice. I added them when I did B's, that's why they have arrows here, and I added them when I had C's, so I had that. So I better subtract it again. So minus B intersect C. Same thing here, A intersects C. I did it twice. You see there's arrows, there's lines going this way and there's lines going this way. So it's minus A intersect C. Okay. Now, hold on 1 second. Let's look at this middle region, which is on the intersection of all three of them. I added it once with A. I added it twice with B. I added it 3 times with C. Then I subtracted it once. I subtracted it twice with these intersections, and then I subtracted it 3 times. Once, twice, and 3 times. This middle thing is in all 3 of these things. So I added it 3 times and I subtracted it 3 times. Well, if I want to complete adding, so right now there's nothing there. I didn't add in those things that are on there. So you better add it in again. Okay? And so you get A intersect B intersect C. Okay? So you have a bunch of additions and subtractions. Okay? And of course the book does, but we're not going to do it. You're going to look it up in the book. What happens if you have A intersect A union B union C union D? Okay? And there's a rule. It basically goes as follows. If you have one thing if you're intersecting one thing like this, or I'm sorry, if you're intersecting odd things like this, 1, 1, 1, or 3 is 1, then you add it. And if you're intersecting even things like this, 2, then you subtract it. And now you can build this up forever and ever. Okay, but obviously, you know, this is going to have a lot of different pieces. And again, it's in the book and you should look at it, but it's not so pleasant to actually write out. Okay, we're going to do problems with that in a second, but it's just like we did problems with these. We're going to be given some pieces of information. We have to get the other pieces of information. Nothing hard. Okay, so we're going to be given this, this, and this, and we have to figure out this, or something like that. And same thing here. We're going to be given, you know, this, 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 and we have to figure out that, or something like that. Okay? Great. That's pretty much the inclusion-exclusion. So you're including things, you're excluding things, you're including things, you're excluding things, odd and even, etc., etc. Let me just show you something else. So fine. Again, we'll do examples later on of using this thing, but that's not important. Great. Let's talk about the binomial methods. And the idea is that these n choose r show up lots of different places, and we want to explain where they show up. Okay, so one of the places they show up is in polynomials. So this is called a binomial. Well, it's in polynomials. So let's just say I do a plus b to the nth power. I want to write this out. So this is a plus b times a plus b times a plus b times a plus b. Okay, n times. Okay, now when I'm multiplying this out, okay, you're familiar with what happens when I multiply out two of them. Okay, so in 9th grade you learned about FOIL. So basically it's F times first times outer times inner times last. But what you're really doing is you're multiplying everything in here times everything in here. And when you have three of them, you're doing the same thing. You're going to multiply this times everything in here. Every one of these guys is going to be multiplied by every one of these guys, and the result of that is going to be multiplied by every one of these guys. Okay? So too here. You want to multiply. A is going to be multiplied by everything else. B is going to be multiplied by everything else. But you have to unite common terms. Okay, so you might ask yourself, what? Okay, the main point is, oops, sorry. The main point is, you're going to have a term with RA's in it. Okay? You're going to have a term with RA's in it. Now, the other terms, the things that you don't, the times that you don't choose the A's, what are you going to choose? You're going to choose B. So it's going to be B. And how many times do you not choose A? Answer, n minus r times. Okay? Okay, so now the question is, how many times are you going to see this term written out? And the answer is as follows. N choose R. Okay, let's see why. Because you're going to have n terms here, and you want to choose, you want to know how many times you're going to choose the A's. Well, I could choose this A, and this A, but not the others. I could choose this A, and this A, but not the others. I could choose da-da-da-da-da-da-da. Okay, so let's just think of this as you have an urn of different terms, and sometimes you're going to pull out the A's, and sometimes you're going to pull out the B's. Question, how many different ways are there of pulling out the A's? Answer, and choose R. Okay, so we can write we can write, so this is going to be the leading term for the A to the, this is going to be the coefficient for this term. So we can write this as follows. Okay. A plus B to the n is equal to the sum of r equals 0 to n of n choose r, a to the r, b to the n minus r. Okay, and you're going to see this again a little bit later on when we do Pascal's triangle, but let's actually do an example. Okay, so it's a clever little thing. It has nothing to, it's just counting. You have to choose A or B here. You have to choose an A or B here. You have to choose an A or B here. You have to choose an A or B here. So this is how many times you're choosing A, R A's. Okay, so let's do an example. As follows: 2 to the x minus y to the 5th power. What the hell is that? Okay, it's equal to the sum of r equals 0, because you can choose none of the x's, okay, to 5, of 5 choose r, of 2 to the x to the rth power. Don't forget you have minus y. This I specifically chose minus y, okay, to the 5 minus r power. Okay, so let's work it out. So this becomes 5 choose 0 times 2 to the x to the 0th power times minus y to the 5th power, plus 5 choose 1, you're going to choose 1 2 to the x, 2 to the x to the 1 power, times minus y to the negative 4 power, 5 minus, to the 4 power. Okay, 1 plus 5 is 5. 5 plus 0 is 5. We're always going to get 5 there. Okay, plus 5 choose 2 to the 2x to the squared power, to the minus y to the 3rd power. 2 plus 3 is 5. Okay, let's just leave room because I'm going to fill in these values here in a second. So this is plus, we did 5 to the 2, 5 choose 2, so now we do 5 choose 3. Let's write it out. That's 2x to the 3rd power times y minus y to the 2nd power, plus 5 choose 4 of 2x to the 4th power, and that times minus y to the 1st power, plus 5 choose 5, 2x to the 5th power, times minus y to the 0th power. Okay, and now we have to plug this in. So let's do this. 5 choose 0. How many ways are there of choosing 0 things? There's only one way of doing that. 2x to the 0, so this becomes minus y to the 5th power. Should I put around parentheses? Well, minus y to the 5th power is minus y to the 5th. Okay. 5 choose 1. Is plus 5 times 2x times 2x times y to the 4th power, because the minus cancels out. 5 choose 2 is 10 times 4x squared. 2x squared is 4x squared times, so we're going to put the minus over here and we're going to put the y to the 3rd power. Okay. 5 choose 3 is also 10 times 8x to the 3rd power times y squared. 5 choose 4 is 5 times 2x to the 4th power, so that's 2 to the 4th is 16x to the 4th, with the minus over there and a y. Okay, 5 choose 5 is a 1, 2x, so this is 32 times 32x to the 5th. Okay. Anyways, it's a little bit ugly. Let me just write down the final thing. Well, I'll write it on top. You all have this on paper, so you can write it on top. So I get minus y to the 5th plus 5 times 2 is 10x to the y to the 4th minus 40 x squared y to the third plus 80 x to the third y squared. Okay. The next one is 10 times 80. Again, 10 times 4, 10 times 80, 5 times 16. Minus 80 x to the fourth y to the 1. Okay. And finally, 32x plus 32x. Okay. Anyways, it's a nice, easy way of doing it. And it's very nice. Okay, next. So we like these binomial coefficients. That's what they're called, binomial coefficients. We like them. And by the way, in section 5.4, which we're not doing, or maybe we will do in another semester, but we're not doing this semester, they have multinomial coefficients. What happens if you have a plus b plus c to the nth power? Okay, so then you have to worry about different things. Okay, good. Okay, these two objects have this coefficient, this binomial coefficient has two properties. Now I can prove these properties easily algebraically, but I don't want to prove them algebraically. I want you to get the intuition for them. Well, maybe I'll do this. N choose R is equal to N choose N minus R. Okay. Okay. So let me just give you the intuition for it. You ready? You have N balls in an urn. You reach in and you choose out R of them. Okay? So, question, how many ways are there of choosing R balls from N balls? Well, let's just look at what happens there. You have a urn of N balls, you choose R of them. So one thing is what you have in this hand, you have R of them. But let me ask you, how many balls are left in the urn? Answer, N minus R balls. So choosing R balls is the same thing as choosing N minus R balls. Okay, that's exactly what that says. The number of ways of choosing R balls is the same as the number of ways of choosing N minus R balls. Okay, but of course you can do this just algebraically. In other words, you can write this as the formula. So this becomes N factorial divided by N minus R factorial. And this is combinations. We don't care about order. We divide out by order. So that's R factorial. As opposed to that, this is equal to N factorial divided by N minus R. N minus N minus R. So let's write that out. N minus R. Take that whole thing factorial. Divided by N minus R factorial. Well, what's this? N take away N is 0. Minus R is R. So this thing becomes R factorial. So you have on the top you have N factorial. On the bottom you have N minus R times R times R. So that's the same thing. Great. Next, there's another property that's also can be done the same way. It goes as follows. N plus 1 choose R is the same thing as N choose R minus 1 plus N choose R. Okay. I'll read this. Okay. Now again, I could sit down and write down what this is. write down what this is, write down what this is. I'm going to get different fractions with different things on the bottom. I can make those fractions equal each other, and then I can actually add them and show that they're the same thing. Okay? But I want to instead do a different way. You ready? I have, in this urn, I have n plus 1 things. Okay? Now, I'm going to call this guy, I have n plus 1 different balls in my urn. Okay? I'm going to call this guy the nth plus 1th element. Okay? He's my n plus 1th element. So he's maybe my first, second, third, fourth. Great. Question. I have n plus 1 balls in my urn. I want to choose r of them. How do I choose r of them? Well, there's two possibilities. One possibility is choose this one. In other words, some of the times that you choose r, you're going to choose this one. So let's see what happens when I choose this one. Now I'm choosing r elements. One of them is this, so let's forget about that. So now, how many ways can I choose? If I already chose this one, how many other ways do I have? Well, answer, I have n left over, and I want to choose r minus 1 of them, because I already have one of them. So I want to choose r minus 1 of them. That's one possibility. Okay? So, if I want to have n plus 1 guys, one possibility is choose this one, and then from the rest you have n balls left, and you want to choose r minus 1 of them. The other possibility is I'm not going to choose this one. When you reach in, you can either choose the n plus 1th or not. Well, what happens if you don't choose it? Then you're choosing r balls, you're going to have r of them left, and you can have n of them left because you're not choosing this one, and you're going to choose r of those n balls. So this works out. The intuition makes sense. Okay, in some sense we did this before with you're describing the new in terms of the old, and you're going to see this in a second. Okay, so again, we can write this up very nicely algebraically, but the intuition makes sense, and it might be an idea to re-listen to it. Well, let's just say it again. Ready? If I'm going to have n plus 1 guys, and I want to choose r of them, I can either choose this one or not choose this one. If I do not choose this one, then I have n guys, and I'm choosing r of those left over. How many ways are there of doing this? If I do choose this, then fine. I still have to choose r minus 1 of the leftover guys. That's why that says. Okay, so great. Now, using these two rules, we get something that's about 500 years old, and that's called Pascal's triangle. Okay, there was a guy named Blaise Pascal. Okay, he was very bright, and he did a lot of mathematics. Anyways, so Pascal's triangle looks something like this. 0, 0, 0. 1, 0. Sorry. 1, 1. 2, 0. 2, 1. 2, 2. 3, 0. 3, 1. 3, 2. 3, 3. 4, 0. 4, 1. 4, 2. 4, 3. 4, 4. Dot, dot, dot. And this goes on. Okay? But the thing is, using that trick, we can write it. If you have 0 balls and you choose 0, how many do you have? You have 1. Okay? Okay? Great. Now, this basically says that rule that we saw, n plus 1 choose r is equal to n choose r minus 1 plus n choose r. Okay. What that says is that in order to determine that, well, this is, anyways, this is a 1, this is a 1, this is, okay. In order to determine the 2, 1 thing, look at the 2, 0, the 1, 0 thing, and then add it like this. Okay. And so this becomes a 2. Okay. Now, those things with a negative bottom, where these numbers are, where r is, or r minus 1 is negative, is 0. So you might think of zeros all the way out here. You might think of zeros outside. So this guy is 0 plus 1, which is 1. And this is a 1. Okay? And here we do it again. This is a 0 plus 1 is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1. Okay? 1, 4, 6, 4, 1. Okay? And we can just go on. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. 1. Etc. etc. Okay? But now we did to the 5th power, so you saw those exponents were, those leading coefficients is 1, 5, 10, 10, 5, 1. Okay? And the fact that the other rule that we had there shows that this is somehow symmetric along the middle. In other words, whatever is true on this side is true on this side. Great. Okay. Great. Let's erase this. So we're gonna use this trick to find out, to solve a lot of things. Great. I just want to do homework number 11. And it says as follows. Well, we want to use this 1 plus 1 to the nth power. Well, what's that equal to? Okay, this is equal to the sum of n to the I going from 0 till n, of 1 to the n, 1 to the I times 1 to the n minus I. Okay, well, 1 to the I times 1 to the n minus y, whatever, that's just 1. So this really shows is that 2 to the n, 1 plus 1 is 2, 2 to the n is equal to, okay, again, these all become 1s, so this becomes n choose 0 plus n choose 1 plus n choose 2 plus n choose 3 plus plus n choose n minus 1 plus n choose n. Okay, that's just writing this out. Okay, now that's algebraically true, but I'd like to understand how it works. And the idea is something we've seen before. You ready? I have n elements. I have an urn of n elements. I want to choose subsets. When I'm reaching in and pulling out r things, I'm pulling out a subset of r things. Great. Okay. Now I want to ask the following question. How many subsets are there altogether? Well, we know this. We know this from the first semester, first day of class. We say, what did we write? We wrote the power of S, number of elements, is equal to 2 to the number of elements of S. Okay, so we saw this. The number of subsets altogether is 2 to the S, 2 to the n. Okay, great, for any set, for any finite set. Great, but I want to think of it as another way of thinking of it. 2 to the n subsets, you can have subsets of size 0, or subsets of size 1, or subsets of size 2, or subsets of size 3, or subsets of size n minus 1, or subsets of size n. It's a way of splitting up all your subsets. Okay? And that's a very clever thing to do. Okay? But it's just two ways of seeing things. One is following the, the rule we had, and the other one is to just intuitively, what does it mean? All 2 to the n subsets are of a certain size. I'd like to know, and these tell you the sizes of those subsets. Sounds good. Next. Okay. The next one is something we're going to use in the book. It goes a little bit wild over this, but that's fine. Okay, they use this over and over again. It's a brilliant little example, but it's fine. You ready? I have $7 bills, and I want to give it to 3 people. The 3 people are 3 different people. Okay, here's person A, person B, and person C. Okay, the dollar bills, I don't care about the dollar bills. I don't care which one of the $7 I give to him, and which one of the $7 I give to him, and which one of the $7 I give to him. Obviously, they're not identical dollars, but to me, because they have different numbers on them, but to me, they're all the same. Okay, so here's the thing: you want to give $7 to 3 people. Okay? And you want to know how many ways we're counting, how many ways are there of doing this. Okay? And the way to think of it is as follows. You have 3 people standing there. Okay? And you can give it out as follows. 1, 2, 3, 1, 2, 1, that's 5, 2. 3 plus 5 plus 2 is 7. I can give it out like this. Or I can give it out like this. Or I can decide this guy's not getting any money, and I can give it like this. Or I can decide this guy's not getting any money, and give it out like this. Okay? There's a lot of different ways of giving it out. Question: how many different ways are there of giving it out? Okay? And the book has a clever little way of writing these out. It says like this. Take your $7, and take your 3 people, and make 7 plus 3 minus 1 dashes. 1, 2, 3, 4, 5, 6, 7. 7 plus 3 is 10, minus 1 is 9. Okay? So we're going to make 7 plus 3 minus 1 dashes. Okay? Now, I'm going to describe this way of separating it as follows. 0, 0, 1. That's a barrier. 0, 0, 0, 0, 1. That's a barrier. 0. Okay? Okay? This way of distributing the dollars will be represented by this. Okay? Let's do another example. How do I represent this? Okay, where he gets $3, he gets $4, he gets nothing. Okay, that gets represented as, okay, again, I have 7 plus 3 minus 1 dashes, and I'm going to represent this as 0, 0, 0, 1, that's the barrier, 1, that's that barrier, 0, 0, 0, 0. Okay, conclusion. You want to do one more? Let's do one more. Okay. 1, 1, 2, 3, 4, 5. Okay. I'm going to represent this as 0, 1. That's the barrier. Then 0, 0, 0, 0, 0, 1, 0. Okay. So the minus 1 is because if I have 3 boxes, to separate the 3 boxes, I only need 2 lines. Well, that's exactly what's going on here. Okay, great. So, question. How many ways are there of doing this? Answer, I have 7 plus 3 plus, minus 1 dashes, okay, and I want to choose from them, well, I can choose how many zeros, but I'm going to choose 3 minus 1 of those dashes. I'm going to put ones in. All the rest, I'm going to put zeros in. So another way of saying this is, I have 7 plus 3 minus 1 dashes, okay, and I want to choose where to put the 7 zeros. And the other ones are going to be the ones which represent the boundaries, the separations between them. Okay, so that's the example. Okay, so let's now generalize to regular things. Okay. The number of ways of placing n identical, notice the zeros, I don't care what they look like, they all look the same. It's like the dollar bills, they all look the same. 7 identical objects into k different boxes is, so the number of ways of placing n identical objects into k different boxes is, you ready? Well, how many dashes do I need? Well, I'm going to have n objects and they go into k, but in order to separate the k different boxes I need k minus 1 barriers, so I do n plus k minus 1, okay, and I want to choose the barriers, so choose where to put the barriers, so that's k minus 1. Okay, great. Let's look at problem number 8 in the book. Don't move. How many different mixes of candy are possible if a mix consists of 10 pieces of candy and 4 different kinds of candy are available in unlimited quantities? How many different mixes of candy are possible if a mix consists of 10 pieces of candy and 4 different kinds of candy are available in unlimited quantities? Okay? Okay. Anyways, the idea is as follows. Let's erase this. The idea is as follows. You have 4 types of candies. Okay, let's read that again. You have 4 types of candies. You want to choose some of these, some of these, some of these, some of these, such that you get out 10. Okay, 10 is all together. So again, so I'm going to have 10 balls in here. Okay, so this 4 plus 5 plus 3 plus 2. I'm going to have 4 of this type, 1 of this type, 3 of this type, 2 of this type. Okay. Anyways, the answer is 10 plus 4 minus 1. And again, choosing, I think this is a 4 minus 1. Choose the 4 minus 1 barrier. Here's a barrier, and here's a barrier. Okay? Okay, great. Great. Let's do number 15. How many ways are there to put 14 objects in 3 boxes with at least 8 objects in 1 box? Okay, so we need to erase. Okay, so imagine this, you have 14 objects. You want to put them in 3 boxes. Okay, let's read that question again. How many ways are there? This is 15A, sorry. How many ways are there to put 14 objects in 3 boxes with at least 8 objects in 1 box? Okay, so the idea is as follows. Let's say I put 8 objects in here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. How much are left? Answer 6. Okay, there are 6. Now 14 take away 8 is 6. Okay, now the 6 can go here, or can go here, or can go here. They can be split up. Okay, so I could take this other 6 and I could put 2 here, 2 here, and 2 here. I could put 3 here, 1 here, 2 there, etc., etc. Okay, now that's if the 8 are over here. But where else could the 8 be? Well, I could put all the 8 over here. I could put all the 8 over here. Okay, so basically the answer to 15A is 3, because there's 3 possibilities where to put the 8. And then what's left is you have 6 other things, identical things, and you want to put them into 3 boxes. So it's 6 plus 3 minus 1. Okay, because 3 minus 1, you have 2 barriers to describe that. Okay, choose 3 minus 1. Great. Okay, let's do part B. How many ways are there to put 14 objects in 3 boxes with no more than 7 objects in any box? No more than 7 objects in any box. See, the word no is there. Okay? So the word no is there, so we have to think about that. Okay. Again, you can have 14 objects. You want to put them in 3 boxes. Okay? But no more than 7 is in there. Okay, so one way of doing it is as follows. Look at how many ways of doing this. Hold on. Okay. 14 plus 3 minus 1. That's how many ways of, so I have 3 minus 1. That's how many ways of putting 14 objects into 3 boxes. That's simple. But we want no more than 7 in every box. So what we have to do is subtract and count out those that don't work, okay, that do have more than 7. Okay, so that do have more than 7, and the answer is as follows. Well, so we want to subtract out those that have 7 or more. No more than 7. So it's not more than 7, it's 8 or more. Sorry, let's read the question again. How many ways are there to put 14 objects in 3 boxes with no more than 7 objects in any box? So we have to make sure that there's no 8 in any box. Okay, so it's minus. Okay, how do you put 8 in any box? Well, there you could put 8 in here, etc., etc. So basically, we just did that. Okay, so it's 6 plus 3 minus 1, 3 minus 1. Okay, and again, the 3 is because the 8 could be in here, the 8 could be in here, the 8 could be in here. Okay, that's the final answer. Of course, you have to work out the answer. This is, you can write this out. 14 plus 3 is 17 minus 1, so it's 16. Choose 2 minus 3. Choose 6 plus 3 is 9, minus 1 is 8. Choose 2. Okay. Let's do 15C. Let's 15C. Okay, hold on. It's 15C. For how many numbers between 0 and 999 is the sum of their digits equal to 20? Hint, each digit must be at least 2. Okay, and the idea is as follows. All the numbers from 1, 2, 3 to 999, all the numbers from 1 to 999, okay, you can write the number 732 as something like this. 1, 2, 3, 7, 732. Okay, so think of it that way. Okay, good. Now let's read the question. For how many numbers between 0 and 999 is the sum of their digits equal to 20? Sum of their digits equal to 20. Now, what's the sum of the digits here? 7 plus 3 plus 2 is 12. Not enough. Okay, so let's do this. How would you get the sum of the digits to be 20? Well, you want to put in 20 elements here. Okay, let's read the question with the hint now. For how many numbers between 0 and 999 is the sum of their digits equal to 20? Hint, each digit must be at least 2. Each digit must be at least 2. Oh, well, okay, fine. So basically, what you want is, you want 20 elements, and you want to separate them into here, into here. Okay. Well, let's just see what doesn't work. I can't have 0, 0, and 20 here, because that's not one of these digits. Okay. Let's see. Can I have 1, 1, and 18 here? No, I can't. Okay. Okay. So let's find a number. How about this? 7 plus 7 is 14 plus 7. 7 plus 7 is 14 plus 6 is 20. So this would work. Okay. Okay, 776 would work. What is it talking about? At least 2. Okay. Hold on. Okay, and pays to go through and see what adds up to 20. So 199, 9 plus 9 is 18, 1 is 19, that's not 20. So you need at least a 2 in any one of them. Okay, 299, well that's 21, that doesn't work, but 298 works. Okay, and so you need, each one has to have at least a 2 in it. Okay, actually these are 298, 289, those are possible. Great. Now, what else? So each one has to have at least 2 in it. What can't it have? Okay, okay, and the answer is, let's just do this. If you put 2 in each one, okay, then you want to get, let's do this. So you have 20 elements. You put 2 of them in each one because you're not going to get less than that. You're not going to get anything with a 1 in it. Okay, and so what's left is you have to distribute not 20 but 14. Okay, 20 minus 2 plus 2 plus 2, 20 minus 6 is 14. Great. But we have something else to worry about. We cannot allow anything larger than 9. These are digits of a thing. You can have an 8, you can have a 7, you can have a 9, you can have a 10 as a digit. Okay, so you can have larger than 9. So what you have is as follows. You have 14 plus 3 minus 1. So you have these 14 elements you want to distribute. The 2 already are given. 14 minus 3 plus 1. And you want to choose 3 minus 1 things. But I want to make sure that there's nothing 10 or larger in it. So what I want to do is I want to subtract out those bad ones where you have 10 or more. Well, the 10 or more could go in here, could go in here, or could go in here. Notice I can't put 10 in more than one. I can't have 10 over here and 10 over here, because that would give us already 22, which is way too much. Okay, and so the bad ones are those that have 10 in one of them. Okay, now which one? Could be this one, it could be this one, it could be this one. Okay, now if I have 10, let's say in this one, okay, then how many more things do I have to distribute? Let's see. I put down 2, 2, and 2, so I have 14 left. I put down 2, 2, and 2, but I have 10 in here. Okay, so I have 10 plus 2 plus 2. That's going to be 10 plus 2 plus 2 is 14. Okay, and what I would have to do is distribute the last 6 over. How do I have to distribute them? How do I distribute the last 6? Okay, I guess I would do 6 plus 2 minus 1. Okay, 2 minus 1. Well, I'm just being, so if I put the 10 over here, then I can do this. But this is just 6 plus 2 is 8 minus 1 is 7. 7 choose 1, that's just 7. The 7, look, I have 6 other things, so I can put some of them in here and some of them in here. Think of them as putting, well, how many different ways are there of partitioning it? So that's, anyways, that's the answer. Okay, great. So that's it for section 5.3, and that's it for the course pretty much. Now I'm going to add one more video that gives you the answers. I want to go through all the questions of section 5.1, 5.2, 5.3. So we're going to do that right now. Well, whenever I get around to it. But there will be an answer. Now, basically, we did the even number problems, and in the homeworks we do the odd number problems. So you see a lot of these problems. Anyways, have a wonderful semester.